So our next topic is sketching graphs of functions. So a function in the form a times f of x, where our x is k x minus p, plus q, can be graphed by analyzing the transformations that the function y equals f of x has undergone. If a is less than 0, then the base graph is reflected in the x-axis. This means if you had a parabola that opens up, that we would reflect it in the x-axis to get a parabola that opens downwards. Also note the graph is vertically stretched by a factor of the magnitude of a if the magnitude of a is greater than 1, or it's vertically compressed by a factor of the magnitude of a if the magnitude of a is less than 1 or greater than 0. So you can think of it this way. If you're multiplying by a number bigger than 1, say 2, of course you're going to stretch the graph. If you're multiplying by a number, say 1/2, you're going to make the graph half its height, so you're going to compress it vertically. We're going to take a look at this note later. Next, if k is less than 0, then the base graph is reflected in the y-axis. And what this could look like is if you had your square root function here, and I had a negative k value, it would be reflected across or in the y-axis. The graph is also horizontally stretched by a factor of 1 over the magnitude of k if the magnitude of k is less than 1 or greater than 0. And it's compressed by a factor of 1 over the magnitude of k if the magnitude of k is greater than 1. Again, we're going to take a look at this note afterwards as well. Next is our q value. If q is positive, then the graph is translated up by q units. And if q is negative, then the graph is translated down by the magnitude of q units. Again, we'll look at this note later. And finally, the p-value. If the p-value is positive, then the graph is translated right by p units. And if the p-value is negative, the graph is translated left by the magnitude of p units. And again, we'll look at this note in just a moment. So let's review how to graph a function using transformations. So example 1, we're going to graph the parent function root x and the transform function g of x equals negative root of 2x plus 5 plus 3. So let's start with the root of x. So here is the base graph for the root of x. It's 0, 0, 1 and 1, 4 and 2, and 9 and 3. So what we have here is g of x, which remember our a value stays outside of the function. Our k value is inside of the function, as well as the p value, and the q value stays outside. So what I like to do is work from left to right. So we're going to start with the a value, then deal with the k value, and then deal with the p and q values. So starting with the a value, we see the a value is equal to negative 1. So our first graph is going to be y equals the negative of the root of x. So we're going to apply the a value first. And what this means is we're going to multiply all of the y values by negative 1. So our y value that was 1 becomes negative 1, 2 becomes negative 2, and 3 becomes negative 3. 0 stays as 0. So there is our second graph. Sorry, I should include the first graph, y equals root of x. And our second one was y equals negative root of x. Next, we're going to apply the k value. So y equals negative, and the k value is 2. What this means is I'm going to multiply all the x values by 1 over 2, or I'm going to compress them all by a half. So therefore, this x value at 1 and 1, it becomes now 0.5 and 1. The next one at 4 and 2 becomes 2 and 2, and 9 and 3 becomes 4.5 and 3. So here is the function compressed by a factor of 1/2. And finally, we're going to apply our p and q value to get our final function g of x. And this one is saying move left 5 and up 3. So we go 1, 2, 3, 4, 5, 1, 2, 3. Here is that starting point. There's our next point, our next one, and our final point there. So I've moved the red graph to the left 5 and up 3. And there is our final graph, g of x. Once we're done graphing this, we should state our domain and range. So we see our domain is that x can take on any real number. However, x has a restriction where it has to be greater than or equal to -5. Similarly, we have our y values can take on any real number. However, the restriction for the y values is that y has to be less than or equal to +3. So there's the domain and range for our green graph. Now this can be tedious with more complex functions, and sometimes it's hard to find the points. So a new method we're going to use is just go directly from the parent function to the transform function. And let's think about how we can do that. Remember, we started with the points x and y. So if we think about what a, k, p, and q do to the function, we can then come up with a formula to get the transform points and the final graph. So let's start with the a and q, the object outside of the graph. They affect the y value. Think of it this way. I'm taking the function, the square root function, multiplying it by a, and then adding q. So what I'm doing is I'm taking my y values, I'm multiplying them by a, and adding q. What about the x values? Well, with the x values, I'm dividing by k, and then adding the p values. Because remember, the a stretches or compresses vertically, the q moves up or down, so that affects the y. The k value stretches or compresses horizontally, and the p value moves the graph left or right, so those affect the x. So what we could do is simply take every point on the base graph and apply the transformations using the following formula. So let's try that for the next example. So notice our next function we have is a cubic function. How do we know? Because of the cube sitting right there. So let's start by drawing our base graph. And let's draw our base table. So for us, we'll just choose values of -2, 1, 0, 1, and 2. Which we know are -8, -1, 0, 1, and 8, if we cube each of those values. So this is our base graph, y equals x cubed. Next, we're going to apply some transformations to get our new set of points. So again, we're starting with the xy points given here on the left, and then we're going to apply some transformations to get the new points. So remember, the k and the p affect the x. And what we have is x divided by k, so in this case k is -2, plus the p value, which in this case is -3. And then for the y's, we're going to multiply by a, so we have 1/2 y, and then add the q value, which is -4. So here's a formula that will take all our x's and all our y's and convert them into the transformed points. So starting with the first point, we have x equals -2. So we sub that in, I get -2 over 2, which gives me +1, minus 3, which tells me that my first point is going to occur at negative 2. Next is to sub in the y value. So 1/2 of negative 8 is negative 4, and negative 4 minus 4 is negative 8. And then we keep going through those points, so try them yourself. So here are all the transform points. The next step is to plot all these points. And here's our graph, y equals f of x. All the transform points. And we can see that it's compressed by a half vertically, compressed by a half horizontally, reflected across the x-axis, and then shifted 3 units to the left and 4 units down. So let's state our domain and range. So for a cubic function, the domain is x is any real number, and the range is that y is any real number. Next one. This time we only have 2 points. So this would be hard to graph using transformation. So let's plot the 2 points first. So we have negative 3 and positive 1. And then we have 2 and negative 1. That's it. That's our whole function. So now let's apply our transformations. So first of all, let's write out our table. So we have negative 3 and 1, 2 and negative 1. And we're going to apply some transformations to get the transformed points. So remember, for the x, we have to apply the k and the p. So remember, we're going to divide by the k. So if we divide by a third, that's multiplying by 3. So I get 3x and then plus 1. And then for the y value, I'm going to multiply by negative 2 and add 4. That's the a and the q. So we look at our transform points. 3 times negative 3 plus 1. That's going to give us negative 8. And then negative 2 times 1 plus 4. That's going to give us 2. So I took these 2 points, subbed them into this formula, and out came these 2 points. Keep going from there. If I have 2, negative 1, I should end up with 7 and 6. So let's plot those 2 points. And there are the 2 points for our final function. Domain and range. Domain is that we have the x values negative 8 and 7. And that's it. The range, so the y values are 7 and 6. Or if we put them in order, 6 and 7. So again, we could talk about in words. If we took a point from the original graph f, we would have to stretch it by a factor of 2, reflect it across the x-axis, then stretch it by a factor of 3 horizontally, move it 1 to the right, and 4 points up. And that's what we've done just by using this formula. All right, next one is the absolute value of x. So let's start with the base graph. So again, we have x and y. So we'll do negative 2, 1, 0, 1, and positive 2. And we end up with 2, 1, 0, 1, and 2. Remember, the absolute value function is the distance from 0. Let's now get our transform points. So again, x and y. So we have these points x and y, and we're going to convert them, first of all, by taking our x values and dividing by k and adding p. We're going to take our y values, multiply them by a, in this case a is 1, and then add 1. So there is our formula to get our transformed points. This f here just means function. So what they're saying is that g of x is the same thing as the absolute value of negative 2 x minus 5 plus 1. So notice the a value is 1 for this example. So next is to get our transform points. So you can try that yourself. So you get 6 and 3 5.5 and 2, 5 and 1, 4.5 and 2, and 4 and 3. So let's graph these. So there is our final graph G. And there's F. So again, if we think about it in terms of transformations, we're going to compress this horizontally by a factor of 2. That's why the V looks more narrow. We're going to reflect it across the y-axis, so the V still looks like a V if you reflect it across the y-axis. Then we're going to move it 5 units to the right and 1 unit up. So finally, let's state the domain and range. So we know x can be any real number for our domain, and y can be any real number. However, we do have a restriction, and we see that y has to be greater than or equal to 1. That's the lowest point of the graph, and then it continues upwards. And our final graph, an exponential. Let's start with our base values. So I would just go from -2 to 2 for an exponential. Remember, your base chart will depend on what graph you're dealing with. Since our base function is y equals 2 to the x, we have 1/4, 1/2, 1, 2, and 4. Remember, this one has a horizontal asymptote at y equals 0. So we're going to take our xy points now, and we're going to transform them using our formula here. So this one, the k value is -1. If we take x and divide by the k value of -1, we get -x. We have no p value, so we're done there. But we do have a q value. So in this case, we're going to get y plus 3, and that's all we need to do. So for an exponential function, just as a side note, would look something like this. Y equals a 2 to the k x minus p, and then plus q. So now let's get our transform points, x and y. So our x values just change sign, and our y values, we just add 3. Finally, let's graph this exponential function. Now remember, this has to have a horizontal asymptote, but since we shifted it 3 units up, our horizontal asymptote is also going to move 3 units up. So we have a new horizontal asymptote. So let's go to our domain and range. So domain for an exponential, we can always sub in any real number. And the range for an exponential, since we have a horizontal asymptote, we definitely have a restriction. So y can be any real number. However, y has to be greater than 3. It can't equal 3, but is greater than 3. So for homework, please try the following questions from your textbook. And can you rewrite a quadratic in standard form in vertex form? So review how to do that, look it up, see what you remember. If you have any questions, please ask.